Swayam Prabha. Digital India. Educated India.
Welcome to lecture number 1 in stability analysis of slopes. In previous lectures, we have seen the applications of shear strength theory, that is earth pressures. Now let us look into how we can analyze slopes with the knowledge we have learnt. In this lecture, we look into predominantly types of slopes, failure types and causes of slope failure, and some analysis methods for slopes. So, you might have learnt this shear strength theory. With that, two possible aspects which are very important. One is earth pressure theories and stability analysis of slopes, and these two are entirely rely on the shear strength of a soil. So, in earth pressure theories, we understood how we can compute earth pressures on a retaining wall. Now, in these lectures, what we look into is how we can analyze a slope or arrive at a safe slope in case if the slope is unstable, and we look into methods for enhancing the stability of a slope. So, predominantly there are two slopes, one is infinite slope, other one is finite slopes. The infinite slopes, the slope that extends over a long distance and the conditions remain identical along some surface or surfaces for quite some distance. That means, the slope which can extend over a long distance and the conditions remain identical, that means that properties remain identical along some surface or some surfaces for quite some distance. Whereas, finite slopes that connect land at one elevation to land that is not far away, but is at different elevation. That means that this connects the land at different elevations. This can be natural or man-made. That is, this can be a natural hill slope or a man-made slope like highway embankment or railway embankment or railway cutting or so. So, in this slide what we learnt is that the shear strength theory can be applied to earth pressure theories and stability analysis of slopes. And we said that predominantly there will be two slopes, and one is infinite slopes and finite slopes. Infinite slopes we define as a slope that extends over a long distance and conditions remain identical along some surface or surfaces for quite some distance. Similarly, finite slopes, the slope that connect the land at one elevation to land that is not far away, but is at different elevation. This can also exist in nature and man-made. So, types of slopes, when you look into it, now let us categorize them. They can be natural and man-made slopes like hillside and valleys, and which form the natural slopes, and coastal and river cliffs are examples of the natural slopes. Examples of man-made or artificial slopes are cuttings and embankments for highways and railroads, earth and ash pond dams where we store coal ash, and that is called ash pond dams, and temporary excavations, waste heaps or landfill slopes which are increasing in the modern world, and landscaping for the site development, that is for the development of the site, the landscaping can create artificial slopes. So, these slopes, man-made slopes, they predominantly cuttings and embankments for highways and railroads, and earth and ash pond dams and temporary excavations. Waste heaps, predominantly they are called landfill slopes, and landscaping for site development. How these slopes fail? We look into the typical types of failure, then we also look into some typical slope failures which can occur in the field. So, types of slope failure, this is a typical circular failure can occur as if like a scoop. So, in this particular mass is moving about a certain point in the space. So, there will be instability. The moment there is instability, then slope tries to move from higher elevation to lower elevation, tries to adjust to a safe slope. So, this is called a rotational slip, and this can be non-circular and circular. Suppose in case of stratifications where the soil varies from place to place, and in such situations some non-circular failures types are possible. So, typically the slope failure is characterized as a circular failure for convenience, and also the assumption that with the mobilized shear strength is uniform, with that assumption which can be said as circular failure can be predominant. And some type of slopes which are flat, but can have a translational slides like this which is shown. This broken line indicates a failure surface almost parallel to the slope surface. So, in this quite resembles an infinite slope. So, this is a translational slide which actually shows in this type of failure, get detachment here and then get detachment here, and the entire slope moves down the slope. In some cases, if there is a rigid stratum, that is like a stiff clay or a rock, and then it is overlaid by a soft clay or an embankment which has been constructed, with that what will happen is that a compound slip can take place. So, this is how that slip takes place. So, this indicates that this particular portion of the soil is getting detached and moving away from the original soil mass. So, this compound slip is shown here, which occurs or in a typical mode, and as it cannot penetrate through a rigid stratum, it actually will be tangential to the rigid stratum and it erupts out here. So, when this takes place, there will be some settlement here, and because of this, when the failure takes place, there will be a development of a heaving of soil takes place here. In this portion, the soil will be subjected to compression, like the way we have conducted in triaxial test to get the soil properties. That means that if you take a sample from here, and this is the possible failure plane which actually soil can experience under stresses. Here the soil will be subjected to subjected to a tension, or extension here. In this case, this particular interaction almost resembles the way in direct shear test. Now, this resembles something like the analogous to block movement we studied in engineering mechanics. Here, as long as this force is less than mu Sn, the block will be stable. So, consider a block of weight W, and its normal reaction is N. Now, once this block is subjected to a force F1 greater than F, it will be subjected to a movement and it will be continued to move. Moment this F crosses this mu Sn, the block will be subjected to the direction of a movement in the direction of a force. The similar analogy happens when the slope portion moves on a certain surface. So, here the resisting force is the frictional force which is offered by the particular material. So, it depends upon the type of the interface this block has. So, under static conditions mu Sn, but once it is under movement, say F1 is causing the movement to the block, then we can say that mu S changes to mu K, that is kinetic friction. So, in this case, a factor of safety can be defined, a term which is used for knowing whether the slope is stable or not, or on the verge of failure. Say this we can define by using the simple analogy what we use. So, that is factor of safety is equal to Fr by Fd, where Fr is the resisting force and Fd is the driving force. So, in this case the driving force is F and resisting force is mu Sn. So, moment, as long as this factor of safety is greater than certain value, then the slope is said to be, that is, as long as the resisting force is greater than driving force, the particular block or block is said to be stationary. So, as long as mu Sn is greater than F, the block is said to be stationary and there will not be movement. Moment this crosses, then what will happen is that the block will be subjected to a movement. Similarly, the similar analogy happens in the field for slopes, but only thing is that the various orientations are different and types of failure surfaces are different. So, what are the causes of slope failure? Like many causes are there. The first is the gravity, that means that the block or soil tries to move from higher elevation to lower elevation. So, readjustments takes place from higher elevation to lower elevation. Seepage, that is one thing where when the water tries to flow through the soil, then it causes seepage stresses and induces failure to the slopes. Earthquake, erosion, geological features, construction activities like cuttings disturbing the natural slopes or fillings, that is construction of a embankment or a bund on a soft soil can create failure. So, the causes of slope failure can be summarized as a gravity driven one, seepage driven one, earthquake, erosion, geological features, the way the stratifications are there, the way dipping is there, the way the layers have been found out, they actually govern this particular slope failure. And construction activities. We look into one by one how these activities can create a slope failure. So, before that, let us see a typical slope failures, and these are the typical slope failures which are shown because of the continuous inundation of the rains. You can see that how dangerous they are with the onset of the rainfall. This is another case which is shown here, a road portion which is at the after the failure, after a slope failure. So, this is also this picture also shows a slope failure portion of the slope after failure. So, these pictures are shown just to indicate how severe this particular subject, but this particular slope failure can cause to a live transportation utilities for us. Similarly, this particular picture shows landslide damage adjacent to a residential structure. So, you can see here there is a structure or a building very close to that, and the slope surrounding one fails. So, the building which is at the crest of the slope can subjected to distress because of the slope failure, which can induce a failure of the or overtopping of the building also. In this case, a road subsidence caused, and with that how that portion of the road which has got failed is shown, and the cracks development can be noted in the picture on the right hand side of this slide. Similarly, some typical slope failures, even the building which is hanging here, part of the building which hangs here is shown here. So, this building shows how the portion of the building is hanging on a failed slope, and this is a 25-meter high failed slope where this particular slope is underlined by a soft clay, though this material is having a good quality soil, but it is underlined by soft clay that has induced a movement of the failure. So, though the entire portion of the slope or soil slope contains a good soil, but if it is underlined by a weak soil layer, that can induce a failure. So, slope failures depend on soil type, soil stratification, groundwater, seepage and slope geometry. So, these things are very important. Slope geometry in the sense the steepness of a particular slope. So, soil type, soil stratification, groundwater, seepage and slope geometry. Examples of slopes which can be infinite slopes, like we have just discussed that two types of slopes, and one is infinite slopes and another one is finite slopes. There are some cases where these slopes can be categorized as infinite slopes and can be used for analysis, like ore and sandstock piling by dropping from a chute, and embankment formed by end dumping from a truck, natural slopes formed in granular materials where the critical failure mechanism is shallow sliding or surface raveling, and natural slopes formed in cohesive soils with great extent or a weak cohesive soil material on ledge, and slopes in residual soil where a relatively thin layer of weathered soil overlies a firm soil or rock. So, these particular slopes which are formed by this process can be considered as infinite slopes and analyzed by using the method which we are going to discuss for infinite slope stability analysis. Now, as we are discussing the types of slope failure, let us see a translational slide. In this, what happens here is that a failure of a slope along the weak zone of a soil can take place, that can induce a failure of a portion of the soil above it. So, this is a slip or a failure which is indicated, and then this can occur once this resisting forces were dominated by driving forces, that is driving stresses get induce the failure along that weak plane. So, in this translation slide, failure of a slope along a weak zone of soil. So, in this case there is a thin layer of weak soil if it exists, and that can induce a translational slide. Sliding mass travels long distance before coming to rest and common in coarse grained soils. This is quite common in coarse grained soils, or sometimes if there is a deposit where there is a rock outcrop and then there is a deposit of soil above it, that can actually create that along that interface, because of the rainfall with the lubrication of the along the surface, can have a weak plane along that particular interface. So, this type of thin layer of soil can induce that example of whatever we said is the translational slide which can cause. So, here which is shown here, this darkened portion shows that how this thin layer of soil has induced a failure in a certain case. And another type of slope failure is rotational slide, common in homogeneous fine grained soil, and it has its point of rotation on an imaginary axis parallel to the slope. So, this rotational slide has got a point of rotation on an imaginary axis parallel to the slope and somewhere in the space to rotate a portion of the soil to adjust to a safe position. So, there are three types of rotational failure. One is the base slide, other one is the toe slide and slope slide. That is base slide and toe slide and slope slide. Let us look how the base slide failure can take place. So, this is one of the types of the rotational slide. Base slide occurs by an arc engulfing the whole slope, that is arc engulfing the whole slope, and this can occur when there is a soft soil layer resting on a stiff layer of soil, or suppose you have got a soft foundation soil and then you construct an embankment with a strong soil or a stiff soil or a good quality material. In such situation, we can have an embankment resting on soft foundations, a classical failure, base failure can take place. So, occurs by an arc engulfing the whole slope, and a soft soil layer resting on a stiff layer of soil is prone to base slide. So, you can see that how this is the failure arc which is shown, and so this particular portion of soil gets detached and then get tangential to the stiff soil portion which is there. Then the other part of the other type of the rotational slide is toe slide. Toe slide, the failure surface passes through the toe of the slope. So, this type of failure can occur if there is a embankment which is constructed, man-made embankment constructed with poor quality material or with the poor compaction conditions. So, the two failure which actually can occur and then passes through the toe of a slope. And the slope slide, in this case the failure surface passes through the slope, that is the slope portion itself, the failure surface passes and then the slope will be subjected to failure. So, we have seen the base slide, toe slide and slope slide. They are the forms of the different types of the rotation slides, and we have seen how different they are. One is actually passing through the a soft soil and then will be tangential to a stiff soil, and another one is actually within the slope material itself, the other slope or a failure surface passing through the toe of a slope. Another which is classical example in this case of in this subject, which we are not going to discuss in detail, but we can look into this. This is called flow slides, or this type of slides are also possible in some mud slides, which is also called. And here occurs when internal and external conditions force a soil to behave as a viscous fluid and flow down, spreading in all directions. So, you can see that this flow slide occurs when internal and external conditions force a soil to behave as a viscous fluid and flow down, spreading in all directions, and multiple failure surfaces occur and change continuously as the flow proceeds. So, multiple failure surfaces are possible and they change continuously as the flow proceeds. Occurs in dry and wet soils. So, the flow slides are possible in dry and wet soils, but this is the beyond the scope of our lectures. The other one is the block and wedge slide. In this case, block and wedge slide occurs when a soil mass is shattered along joints and seams, fissures and weak zones by forces emanating from the adjacent soils. The shattered mass moves away as blocks and wedges down the slopes. So, this gets detached and moves away from the slope in the forms of blocks and wedges. Then other typical type of failure which is possible in along the hilly slopes, these hilly terrain slopes. So, simple detachment of the rock mass from its parent body, this process is the gravity governed. What will happen is that in case of any minute movements within the slope, and these movements can induce rock falls. So, for this lot of research work is going on to understand or to arrive at the safe distance for locating the transportation utilities. Otherwise, this type of rock falls can create danger to the human lives along that particular areas. So, some of the methods are to induce or to exhibit rockfall warning boards, signboards, or to provide some rockfall catching fences. So, causes of slope failure. In the previous slides, we have seen the types of the slope failures. Now, let us discuss into the different causes of slope failure. First cause, let us discuss this erosion. As we discuss, water and wind continuously erode slopes. So, this erosion can change the geometry of slopes, resulting in a slope failure or a landslide. So, in this particular picture, this is the original stable slope configuration. Once this being unstable, so what happens is that this is being the stable configuration, and this is the toe of the slope and this is the crest of the slope. But due to erosion of a soil, either due to a agency with the water and wind, what will happen is that it tries to form a new steeper slope which may be unstable from the material strength point of view. So, this can induce a movement and induce slope failure. So, water and wind continuously erode slopes and make these stable slopes unstable slopes. That is, they convert the original stable slope into an unstable slope. Erosion changes the geometry of slopes, resulting in a slope failure or a landslide. And other type of erosion which can cause a slope failure is rivers and stream erosion. So, rivers and streams continuously scour their banks, undermining their natural or man-made slopes. So, if there is a embankment constructed along a river, and if the stone pitching is not proper, then it can erode that embankment and create and endanger the stability of a particular slope. In this case, in a picture where a water level is shown, this can be either a river or a stream, and where the local scouring which is shown here, which induces movement in this direction. So, rivers and streams continuously scour their banks, undermining their natural or man-made slopes. So, here the scour by rivers and streams is shown. The another cause of failure what we discussed is rainfall. Many times longer periods of rainfalls saturate slopes, soften and erode soils. So, this is a quite frequent phenomenon which occurs along hilly slope areas subjected to a continuous inundation. So, water enters into existing cracks or tension cracks which are already formed and may weaken underlying soil layers, leading to failure. For example, these mudslides. So, here in this case a picture which is shown here, and this is the continuous rainfall with certain rainfall intensity, and this is already existing crack. So, water enters through this crack, enters a weak layer and induces a seepage force, and because of this the crack filled water induces a water pressure, and then this water entering the weak soil layer tries to lubricate this particular surface and creates and make this entire mass of soil mass as an unstable mass. The another cause which we discuss is earthquakes. Earthquake induce dynamic forces, especially dynamic shear forces, which can occur in very short duration, and that reduce the shear strength and stiffness of soil. So, here these earthquake forces can have in the either vertical direction or in the horizontal direction, and can induce the movement and then induce failure to a particular slope. So, this is the toe and then this is the crest, and this is the movement which is actually initiated because of the earthquake forces. So, earthquakes induce dynamic forces, especially dynamic shear forces that reduce the shear strength and stiffness of the soil, which actually causes a slope failure. So, while in the earthquakes, a phenomenon we should discuss, where one major phenomenon which happens is that called dynamic liquefaction. Here, pore water pressure in saturated coarse grained soils could raise to a value equal to total mean stress. That is, the pore water pressures almost will increase up to whatever the total stress is there at a particular point, and cause these soils to behave like a viscous fluid. Whenever we have learned that whenever this total stress equals to the pore water pressure, the soil loses its shear strength, or because effective stress is 0. So, this phenomenon is known as the dynamic liquefaction. So, structures founded on these soils would collapse. Simply the structures, or say if there is a building or resting on a slope, and initially before this attenuation of these dynamic shear forces, if it is stable, it will actually turn to be unstable because of this phenomenon, dynamic liquefaction phenomenon. The quickness in which the dynamic forces are induced prevents even coarse grained soils from draining the excess pore water pressure. Thus, the failure in a seismic event often occurs under undrained conditions. So, what will happen is that because of the short duration, even for the coarse grained soils, it is very difficult to dissipate the pore water pressure. In such situations, this we can say that under these kind of undrained conditions, where there is no possibility or a time duration for the drainage, then it can occur in the undrained conditions. So, one major phenomenon, the factor, phenomenon which actually governs this earthquake induced failure for a slope is the dynamic liquefaction, and the quickness in which the dynamic forces are induced prevents even coarse grained soils from draining the excess pore water pressure. Thus, failure in a seismic event can occur even under undrained conditions. The another one is that we discussed about the geological features. Many features commonly result in unidentified geological features, like the deposits vary from place to place and region to region. So, what will happen is that there can be a stratification, or like warped clay, you have got a weak soil and then there is a stiff soil and weak soil and stiff soil, and if these stratifications are dipping towards the down the hill slope, and these weak soil layers can actually become like a planar become like a failure surface, and particularly this type of soil stratification, and if it portion of the soil is homogeneous, can have a number of planar failure surfaces possible in some type of shear slopes. And as the construction activities cannot be stopped because of the development, infrastructure development and all. So, we tend to load these slopes due to with external loads, either due to building loads or due to construction of a certain structure on a particular slope. So, these external loadings induce instability to the slopes. So, if there is a overloading at the crest of the slope, that this overloading adds to the instability and creates a movement. So, overloading at the crest of the slope creates a failure, also a causes of failure. So, load placed on the crest of a slope add to the gravitational load and may cause slope failure. So, this external loading which is added at the crest of the slope, if this overloading occurs at far away from the crest of the slope, then we can say that influence is minimal, but if it is within the vicinity of the crest of the slope, then its effect cannot be ignored. The another aspect which we discussed is that construction activities. Construction activities near the toe of an existing slope can cause failure because lateral resistance is removed. Sometimes we do excavations at the toe excavation. So, once that when the excavation is carried out the toe, then we are actually undermining the slope, and what will happen is that it will induce a failure. So, slope failures due to construction activities divided into two cases. One is excavated slopes, and in case of a fill slopes. So, this is an excavation at the toe of the slope. Suppose if this excavation is deep enough, and if it causes this instability, a compound failure can take place, and which induces a movement, entire cutting portion can become unstable. So, when excavation occurs, the total stresses are reduced because of the removal of the material, and negative pore washer pressures are generated because of the removal of the total stress. With time, the negative pore water pressures dissipate, causing a decrease in effective stress and consequently lowering the shear strength of the soil. So, if the slope failure occurs, they take place after the construction is completed. So, these slope failures generally with this type of excavations, they occur once after the construction. So, this is almost the danger, that means that within the lifetime of the structure, and can experience a failure if this process is unstable. And fill slopes are common in embankment construction. If the foundation soil is saturated, then positive pore water pressures are generated from the weight of the fill and then the compaction process. Because of the weight of the fill and compaction process, the positive pore water pressures are generated. So, the effective stress decrease and the construction consequently shear strength decreases. So, the effective stresses decrease and consequently the shear strength decreases. The slope failures in slopes are likely to occur during or immediately after construction, So, we have seen different types of failures and causes of failures. Let us now try to summarize these factors after Gray and Leiser 1982. These are factors that contribute to the higher shear stress. So, the shear stresses are high, that means that these shear stresses can cause the disturbing shear stresses or disturbing forces. So, when the disturbing forces are more, then the stability of a particular slope is in danger. So, what are the factors that can contribute to the higher shear stress? So, removal of lateral support, that is erosion, that is bank cutting by streams and rivers that we have seen. So, that can actually create because of the erosion by streams and rivers can cause something like a removal of lateral support. And human agencies, cuts, canals, pits, etc. can cause this particular failure. And surcharge, natural agencies, like sometimes the slopes get deposited because of the weight of the snow and ice and rainwater. That is when the rainwater gets stored because of some reasons, and weight of the snow, when snowfall takes place, when it is stored for a given duration. So, because of these natural events, then the slopes can get surcharged. Similarly, human agencies like construction of a fill on an existing slope or construction of a building on a natural slope. So, any particular slope can create or cause an external loading to a slope. And transitory earth pressures, that is called earthquakes, that we have discussed, that can contribute to the higher stresses and causing failures to the slopes. And removal of the underlying support, subaerial weathering, so that is solution solutioning by groundwater, that is because of the groundwater minerals, and can cause subaerial weathering, and subterranean erosion, that is called piping, when the water which is flowing through the slope can cause a piping failure and can erode the soil. And human agencies like mining can create removal of the underlying support factor. Lateral pressure, water in vertical cracks, freezing water in cracks, and root wedging can contribute to a reduction in contribute to higher shear stresses. That is, so the major factors, if you summarize, one is the removal of lateral support and surcharge, transitory earth pressures, and removal of the underlying support and lateral pressures. These factors contribute to the higher shear stresses in the and ultimately they cause instability to a soil slope. And let us, having seen those factors, let us see that what are the factors that contribute to the low shear strength. What are the factors that contribute to the low strength? Ultimately, they affect the instability of a slope, cause the instability to a soil slope. Initial state, composition, inherent weak materials. Suppose if there are inherent weak materials, the composition can cause and have a low shear strength. Texture, loose soils and metastable grain structures, which are like say honeycombed grain structure. So these things can cause texture of a soil, like loose soils and metastable grain structures can contribute to the low shear strength. And gross structure like faults, jointing, bedding, planes, warping, etc. This warping or a planes, bedding and jointing and faults, then these are the gross structures within the soil. Changes due to weathering and other physico-chemical reactions, frost action and thermal expansion, hydration of clay minerals, and drying and cracking and leaching, etc. can cause and contribute to the low shear strength. And changes in intergranular forces due to pore water pressure, seepage pressure of percolating groundwater, loss in capillary tension upon saturation, buoyancy in saturated state. So these particular factors can create contribute to a low shear strength. And another this thing is that changes in structure like fissuring of free consolidated clays due to release of lateral restraint, grain structure collapse upon disturbance. So what we have seen is that factors that contribute to the low shear strength, there are initial state, particularly composition, texture and gross structure, faulting and dipping, and changes due to weathering and other physico-chemical reactions, changes in intergranular forces due to pore water, and changes in structure. And these factors can contribute to the instability of a soil slope. Now, having seen types of failure and causes of failure, now we have to learn how this stability analysis of the slopes can be carried out. Basically, these particular methods which we are going to discuss can be adopted for existing slopes or to the slope which is due for construction, like an embankment or a slope for a particular flyover or approach embankment bund which is coming. So if you wanted to decide what is a safe slope, and for that we need the knowledge about this particular topic which we are going to discuss, that is the slope stability analysis. So general assumption is that the failure can be represented in a two-dimensional problem. So here, because like in earth pressures and these particular a particular slope or a canal bund or a cutting or a railway cutting which runs over kilometers, and we can consider this as a plane strain structure. So here what we do is that one of the prime assumptions, even now today the three-dimensional slope stability analysis are available, but for the sake of understanding of the convenience, the failure can be represented as a two-dimensional problem. The sliding mass moves as a rigid body, and the deformations of sliding mass has no significant effect on the analysis. So the sliding mass moves as a rigid body. Wherever it gets detached, it is assumed that the sliding mass moves as a rigid body, and deformations of sliding mass has no significant effects on the analysis. The properties of soil mass are isotropic, and shear resistance along failure surface remains same independent of the orientation of the failure surface. So there can be many orientations which are possible. So, but the properties of soil mass are isotropic and the shear resistance along failure surface remains same independent of the orientation of the failure surface. The analysis is based on the limit equilibrium method. So, and these are the general assumptions what we listed, and they are the failure surface can be represented as a two-dimensional problem, and the sliding mass moves as a rigid body, and the deformations of sliding mass has no significant effect on the analysis, and the properties of the soil mass are isotropic and shear resistance along the failure surface remains same independent of the orientation of the failure surface, and the analysis is based on limit equilibrium method. So, with these assumptions, what we try to look into is that first we will try to see how the infinite slope stability analysis can be carried out, and based on that we look into the different infinite slope stability analysis methods. Once this is discussed, then we can see how a finite slope can be analyzed. See, once finite slope can be analyzed, then we will be in a position to arrive at a safe slope, or if there is an existing slope and we can estimate whether the slope is in danger or whether is having an adequate factor of safety against instability or not. So, let us look into the infinite slope stability analysis method. In this, the basic assumptions which are once again is highlighted. They are highlighted. Soil is homogeneous and the stress and soil properties of every vertical plane are identical. On any plane where parallel to the slope, stresses and soil properties are identical. So, in this case on the right hand side of this slide, a picture is shown, a drawing is shown, where this is the a rigid stratum, or assume that this is a rocky surface and then there is a soil, and this portion from here to here is jet depth is the soil, and inclination of this slope surface is beta with horizontal, and this surface is also assumed that is at the beta with horizontal. And consider a block say B of with horizontal distance is B, and is subject, we say that let us assume that this portion is assumed to we are actually looking to the stability of this particular block. Say let us assume that this is the failure surface, and the failure surface is a planar surface parallel to the slope surface, and this is the location of the water table. This is the location of the water table, and assume that the unit weight of the soil is identical above the water table and below the water table. So, this Z is the depth and HW is the water depth in this direction which is shown here. Please note this direction which is shown here along that is with this particular distance from here to here, this is HW, and from here to here this is Z, and B is the horizontal distance and beta is the slope inclination. So, what it means, this assumption is that the stress and soil properties on every vertical plane are identical. The stress and soil properties on very vertical plane are identical. On any plane parallel to the slope stresses, the soil properties are identical. So, any two vertical planes between a soil portion and between any two vertical planes can be considered. So, on any plane parallel to the slope, stresses and soil properties are identical. Failure in such slope takes place due to sliding of soil mass along a plane parallel to the slope at a certain depth. If this assumption is valid, so then the failure takes place due to sliding of soil mass along a plane parallel to the slope at a certain depth. Having discussed, now let us consider this block having A, B, C, D is the block, A, B, C, D is the block, and Z is the depth and B is the horizontal distance, and beta is the inclination of the line BC with the horizontal, and tangential stress tau down the slope and normal stress sigma within the segment ultimately we determine, but let us look how the weight of the block can be determined. Weight of the segment ABCD is equal to gamma is the unit weight. We assume that the unit weight of soil is identical above and below the water table, Z is the depth and B is the horizontal, and per meter width. So, this is the volume into unit weight, that is the weight of the segment ABCD. Now, the tangential stress tau down the slope can be given by gamma Z B sin beta, that is weight, that is T is equal to W sin beta, that is which causes driving shear stresses, and that is tau is equal to gamma z b sin beta divided by acting over by this area is b by cos beta, because this inclination is beta with horizontal. So, after simplification this changes to gamma z sin beta cos beta. Normal stress sigma within the segment, normal stress sigma within the segment can be given as sigma is equal to gamma z cos beta, that is this particular portion, that normal force divided by b by cos beta, that is this area. So, with that what will get is that gamma z cos square beta is the normal stress sigma within the segment. So, pore water pressure U on the slip surface, that is along this surface U. So, this is HW is this portion and Z is the depth. So, pore water pressure U on the slip surface is given by Z minus HW into gamma W cos square beta. So, with this pore water pressure U on the slip surface is given by Z minus HW into gamma W cos square beta. So, analysis of infinite slopes, we can write normal effective stress sigma dash is equal to total stress minus pore water pressure. Once we do, what we get is that gamma z cos square beta, that is total stress, minus this pore water pressure, we get gamma z minus gamma w z plus gamma w h w cos square beta. Shear strength tau f at the base of the segment along the, that is at the base of the segment, can be given as tau f is equal to c dash plus sigma dash tan phi dash. Tau f is equal to c dash plus sigma dash tan phi dash. So, c dash is the shear strength effective cohesion of a material and phi dash is the effective angle of internal friction. Sigma dash is this effective stress. So, substituting this, what we get is the shear strength of the at the base of the vessel. So, factor of safety, as you know from the shear strength when we discuss, factor of safety can be defined as a available shear strength of material divided by shear stress, that is factor of safety is equal to tau f by tau. Factor of safety is defined as tau f by tau. Tau f is the available shear strength and divided by shear stress, which is tau. So, substituting now for the general case, we can write this expression where factor of safety as c dash plus tan phi dash into cos square beta into gamma z minus gamma w z plus gamma w h w divided by gamma z sin beta cos beta, which is the disturbing shear stress which we calculated in the previous slide. So, with this we have got a generalized expression. Now, we consider different special cases, like let us consider in the analysis of infinite slopes a case like you have a dry cohesionless soil where c dash is equal to 0 and h w is equal to z, that is c dash is equal to 0 and h w is equal to z. That means that it is at the bottom of the that is the at the failure surface, or where there is a rock layer is there at the full depth from the top of the slope surface, there is water table is there. So, in such situation, when you substitute in this particular expression c dash is equal to 0 and then there is z is equal to h w, then what we finally left out is that factor of safety is equal to tan phi dash by tan beta. So, this indicates that the factor of safety of an infinite slope with a cohesionless soil is independent of the depth of the failure plane. So, factor of safety of an infinite slope with a cohesionless soil is independent of the depth of the failure plane. So, factor of safety is equal to tan phi dash by tan beta. So, factor of safety of an infinite slope with a cohesionless soil is independent of the depth of the failure plane. So, for the critical case, factor of safety is equal to 1, that is for the critical case when factor of safety is equal to 1, beta is equal to phi dash, the slope is just stable. That this indicates that the slope is just stable. So, this is a classical example for angle of repose. Suppose if you wanted to form a dry sand heap, then you will not be able to make a slope steeper than its angle of repose. So, this is nothing but factor of safety is equal to tan phi dash by tan b dash, or a classical example which is which can be cited here is formation of sand dunes. Of course, it varies from the windward direction and leeward direction and all, but the one governed here is that the tan phi dash by tan beta, where phi dash is the angle of internal friction of the material and beta is the inclination of the slope surface. So, what we can say that factor of safety of an infinite slope with a cohesionless soil is independent of the depth of the failure plane. And for the critical case, factor of safety is equal to 1, that is beta is equal to phi dash, the slope is just stable. For beta less than phi dash, so let us now plot this particular situation on a tau versus sigma, that is in a Mohr circle, tau versus sigma plot. Let us assume that this yellow line indicates the Mohr failure envelope, and this white broken line indicates the slope surface. This beta is the inclination which is shown here, this phi dash is the slope surface, this is the angle of internal friction, that is phi dash. So, now if you look at a certain depth, then let us assume that this particular point, the coordinates are sigma and tau, and this point is sigma f and tau f. So, for beta less than phi dash, tau is for beta less than phi dash, tau is less than tau f. For beta less than phi dash, tau is less than tau f, the slope is stable independent of the depth of the slope. For beta greater than phi dash, that is beta greater than phi dash, tau is greater than tau f, that means that tau is greater than tau f, the slope would have already failed at all depths. That indicates that the slope would have already failed at all depths. So, we have in this particular lecture, we try to introduce a subject called stability analysis of slopes, which is a very interesting part in geotechnical engineering, particularly in the analysis of soil slopes for understanding about arriving at a safe factor of safety for a structure under conditions like with rainfall and with earthquake and other external loading conditions. And then we looked into the types of failure and types of slope failures and causes of slope failures, and we summarized the factors which can contribute to the reduced shear strength, which can also contribute for the factors which can cause instability to a soil slope. And we looked into analysis for an infinite slope stability analysis, and we have actually derived a generalized expression, and that expression has given us how we can analyze an infinite slope. So, these infinite slope can even can be natural or sometimes man-made because of like waste heaps or ore stacks which are formed and all. So, these can be analyzed. So, a case where case A, what we discussed is called dry cohesionless soil, and we said that factor of safety of an infinite slope with a cohesionless soil is independent of the depth of the failure plane. So, here we have derived factor of safety is equal to tan phi dash by tan beta. So, which is a classical example for a sand dune or a classical angle of repose, which we suppose if you wanted to form a steep sand heap that can never be formed. We observe that always the slope the slopes can gets adjusted and reaches to that angle beta is equal to phi dash.